After we have talked about Boyle's law and Charles' law and Avogadro's law, and let's remind ourselves what Boyle's law says. Boyle's law says that the pressure is inversely proportional to the volume, that the temperature, this is Charles' law says that the temperature is directly proportional to the volume, and Avogadro's law says the volume is directly proportional to the moles, number of moles. I should use that these are not necessarily the same constants, just the constant of proportionality. We have seen these three laws, the experimental laws. The experiment was somewhat easy to do, and these relationships were clear. Now let's see when we consider different gases. And something that was seen fairly early is that all gases such as helium, oxygen, nitrogen, you name it, chlorine, maybe chlorine starts to deviate, but simple small gases, at if they have the same number of moles at the same pressure and temperature, they will occupy the same volume. In this case, the pressure and temperature is what we call standard conditions of temperature and pressure. So every time we say STP, STP stands for standard conditions of temperature and pressure. It means that the temperature is 0 Celsius or 273 should be 0.15 Kelvin, and the pressure is 1 atmosphere. Every time a gas, or what we will say an ideal gas, is at these conditions of temperature and pressure, and you have just 1 mole, the volume will be 2.2.4 regardless of the gas. So 1 mole of helium at these conditions occupies 22.4 milliliters. 1 mole of oxygen in these conditions occupy 22.4 liters, and 1 mole of nitrogen in these same conditions of temperature and pressure occupy 22.4 liters as well. Alright, so this means that these gases, not only helium, oxygen, and nitrogen, but you could say the same for hydrogen, for argon, simple, small gases show a very similar behavior regardless of the formula, regardless of the specific compound these gases are. This is what we call ideal gases. And ideal gases in general are small. That means the compound itself is simple. And this is one of the assumptions, and typically you will see this behavior in which they show the same quantity of volume or the same quantity, the same magnitudes, if they don't interact with each other. They don't interact with each other. So this will typically happen, and we will talk about at low temperatures. All right, these are ideal gases. We say that they are ideal because we consider that their size is negligible and the interaction among them is also negligible. They behave like ideal gases. At the end of this chapter we will talk about real gases which do not behave as ideal, in which their identity needs to be considered. And then suddenly benzene gas may not behave the same way as another gas such as ethanol, so that will not be an ideal gas. But when we talk about small non-interacting gases, they behave very similarly. They are called ideal gases, and when they are ideal gases we can treat them the same way, and we can do something such as putting these three laws together. So notice that we are writing Boyle's law, Charles' law, and Avogadro's law. You can combine them in one single equation. This PV-nRT, being air a constant, and we will talk about its value, contains these three laws: Boyle's law, Charles' law, and Avogadro's law. And notice that this law is applicable to all ideal gases. In other words, to hydrogen, to any small non-interacting argon, neon, you name it, non-interacting gases. Okay, so this equation will be the same for all of the gases, and it will contain the same Boyle's law, Charles' law, and Avogadro's law. Let's see if it's true. It contains all these three laws in this big equation. Let's see Boyle's law. If I move volume to this side, I can see Boyle's law. I can see Boyle's law by doing P is equal to nRT divided by 1 over V. This is Boyle's law, and suddenly the constant of proportion that we saw before that we would just call C, now we know that it's the number of moles times R times the temperature. Charles' law, which was the volume is proportional to the temperature, can be seen if I do nRP times T. Now I know that the constant of proportionality that we were talking about in Charles' law is the number of moles times R divided by the pressure. And finally, Avogadro's law, in which the volume is proportional to the number of moles. See that if I move pressure to the other side of the equal, I get RT divided by P times N. This is the constant of proportionality. Notice that these are not the same, those C that we were talking about, but we are showing that this PV equals nRT can be arranged in different ways so that it still contains in itself the Boyle's law, Charles' law, and Avogadro's law.